You hit the plus 30 seconds button on your microwave.
And you expect hot pizza.
Right, exactly. You get hot pizza. You don't need to know how the magnetron inside that heavy little box is actually generating the electromagnetic radiation.
Yeah, thankfully.
I mean, you don't need to understand the physical wiring at all. You just want the result, and you expect that interface to work perfectly every single time.
And it does, usually.
Right. And it turns out that simple expectation, like knowing how to use a thing without needing to understand exactly how it works under the hood, is basically the only thing keeping the world's software systems from collapsing into total chaos.
Oh, 100%. It really is the defining philosophy of software architecture.
Yeah.
Because, I mean, if you can't contain complexity, you can't scale. You just end up with an unmaintainable web of dependencies.
Which is exactly what we are getting into today. We are decoding the essential principles of object-oriented design to figure out how we hide that complexity. We're looking at excerpts from Chapter 3, Essentials of Object-Oriented Design.
A fantastic source, by the way.
It really is. And our mission for this deep dive is to basically decode these core principles without getting bogged down in all the dense jargon. We want to build a simple, beginner-friendly narrative for you to understand how software is sustainably structured.
No PhD required today.
Exactly. Okay, let's unpack this. To understand how we design those massive, scalable systems, we really first have to look at how we hide complexity in the absolute simplest things.
Right, like primitive data types.
Yeah. Think about basic primitive data types. We all know, int for integer whole numbers and float for floating point decimals.
The absolute basics.
Right. As a programmer, you just type a plus sign between two variables, and the language handles the addition.
And we take that entirely for granted, you know? But if you drop down to the machine level, the computer is implementing that addition in wildly different ways.
How so?
Well, an integer might occupy 32 clean binary digits in memory, right? And adding two integers is a very straightforward operation for the CPU's arithmetic logic unit.
It's just simple math for the chip.
Exactly. But a floating point number is stored completely differently to account for the shifting decimal. It usually follows an ID standard with a sign bit, an exponent, and a fraction.
Oh, wow. So the actual silicon is performing an entirely different physical operation to add two floats than it is to add two ints.
Exactly. But the programming language abstracts all of that away from us.
Right. We don't have to write memory-specific logic just to do basic math. We just push the plus button like the microwave.
Yes, that microwave analogy is perfect. That separation, the firewall between the use of an operation and the hidden implementation of that operation, that is data abstraction in its purest form.
Data abstraction, that's a core concept here.
It is. The language designers built that abstraction for primitives so we wouldn't have to think about the hardware. But when you're building custom object types like, say, a customer class or a shopping cart or an invoice.
You essentially become the language designer for the next developer who uses your code.
Exactly. You have to actively build that abstraction yourself.
Which means you're intentionally delaying decisions, right? You're sketching out the high-level logic of your application, like this shopping cart needs to calculate a total, without getting bogged down in the messy underlying details of how that calculation actually accesses the database.
Yeah, it's a lot like effective delegation in a management role, if you think about it.
Oh, that's an interesting way to put it.
Right, because if you run a marketing department, you tell your team what the campaign goals are. You define the operation.
You don't stand over their shoulder dictating which specific font to use in Photoshop.
Or which cells to click in Excel,
Okay.
exactly.
Yeah.
You trust the employee, or in this case the object, to handle its own internal implementation.
So whether you are writing code or managing a team, you define the what and you let them handle the how.
Precisely.
So if abstraction is how we hide the engine of the car, then interfaces are how we make that engine swappable without having to redesign the entire vehicle.
Yes. Interfaces are where you start to see the real power of object-oriented architecture. Because, an interface doesn't actually do anything on its own.
Right, it's just a contract.
Exactly. It's just a contract.
Take a standard iData service interface from the text. It essentially just lists operations, right? Like retrieve data, save data.
Yeah, just empty signatures, basically.
There is no actual code telling the machine how to write a file to a hard drive or query a SQL database. It's just a list of required capabilities.
Right, so your main application code is written entirely against that abstract interface. It's completely blind to the actual storage mechanism.
And the value of that blindness is pretty immense, isn't it?
No, it's huge. Because today, you might wire that interface up to a lightweight local file system while you're prototyping.
Just to get things working.
Exactly. But 2 years from now, when the company scales, you can swap in a heavy-duty cloud database class that implements the exact same interface.
Because your high-level application only knows about save data and retrieve data.
Yes, you swap out the entire back-end engine without rewriting a single line of your core business logic.
Okay, but then let me push back on this a little bit.
Sure, go for it.
Because in the real world of looming deadlines and sprint cycles, things get really messy. Let's say our system is running smoothly with a database service class. Suddenly, product management says we need a new feature to visually display the data diagnostics on a dashboard.
Oh, the classic pivot.
Right. So as a developer, my instinct is to just open up that existing database service class, quickly type in a new display data method, and just ship it. Why should I go through the administrative overhead of creating a whole new interface for one single UI feature?
I get it. I really do. But because that quick fix is exactly how legacy code bases turn into absolute nightmares.
Really? Just from one method?
Yes. If you just slap a display data method onto your broad database interface,
Yeah.
you are forcing every single client that uses that interface to adopt UI operations.
Wait, why is that a problem if they just ignore the method? If they don't use it, who cares?
Because in many compiled languages, changing an interface forces everything that depends on it to recompile and redeploy.
Oh, I see.
Imagine a background server process whose only job is to silently sync data at midnight. If it depends on that broadened database interface and you add a UI method to it, suddenly that background server is tangling with display logic it will never, ever use.
You've created a fragile dependency.
Exactly. You're coupling things that shouldn't be coupled.
It's like forcing the microwave to also have an interface for brewing coffee.
Yes.
Suddenly, the internal wiring is crossing over, and a coffee leak breaks the magnetron.
That is a terrifying kitchen appliance, but yes, that's exactly the problem. And that's why the text warns us and why we rely on interface segregation.
Keeping interfaces small and highly cohesive.
Right. Instead of bloating the existing one, you create a new, distinct interface called, let's say, iDataDisplay. Your database class can simply agree to implement both of them.
Okay, so the UI components talk to the display interface, the background components talk to the storage interface, and neither knows about the other's business.
You got it. Which perfectly sets up this incredible mechanics subtype polymorphism.
Poly meaning many, morph meaning forms.
Exactly. Because our components are talking to these segregated interfaces rather than rigid, concrete classes, an object's behavior becomes completely swappable at runtime.
And what's really cool is how much runtime flexibility you gain when you stop hard-coding dependencies.
What's fascinating here is that you can actually change how the application behaves on the fly.
Like the classic example from the Java collections framework.
Well, that's a great example.
Let's say you're building a pipeline to process a massive influx of e-commerce orders. The instinct for a junior developer is to write the method expecting a very specific concrete list, right? Like an array list.
Right, which locks you in.
But the architectural principle says no, program to the highest possible abstraction. Expect an interface, like collection order.
Yeah, because by declaring your dependency as an abstract collection, you are actively deferring the decision of how those orders are fundamentally stored and managed in memory.
Right, because you might not even know the business constraints yet. At runtime, if you realize these orders need strict first-in, first-out processing, you can just pass in a queue implementation.
Yep.
But what if there's a glitch upstream and the pipeline is suddenly being flooded with duplicate orders?
So you'd have to rewrite your processing engine.
Exactly. You simply pass in a set implementation, which automatically rejects duplicates by its very nature. The high-level code that is iterating through the orders doesn't change a single character.
It just calls the interface method getNext.
Yeah.
And the swappable data structure handles the physics.
It creates this completely resilient boundary. The high-level pipeline is protected from the chaotic, ever-changing details of data ingestion.
It's beautiful when it works.
It is. So we have this elegant system of interfaces and abstraction. It sounds bulletproof. But we both know that software projects still devolve into spaghetti code and catastrophic bugs all the time.
Oh yeah, constantly.
Why does it still break? Usually it's because developers abuse inheritance.
Yes. Inheritance is one of those object-oriented concepts that feels so intuitive to humans, but it completely falls apart when mapped to machine logic.
Because inheritance is a relationship, right? Creating a subclass by adopting all the properties of a parent class.
Right, like saying a dog is a subclass of animal.
Which makes perfect sense in biology.
It does. But when modeling software, That rigid taxonomy is often a total trap.
Take mapping coordinates, for example. You have a point 2D class with an X and Y coordinate.
Standard stuff.
A few months later, the application needs to support 3D space, so you need a point 3D with X, Y, and Z.
And I know exactly what you're going to say next.
The absolute most common developer instinct is to say, well, a 3D point is just a 2D point with an extra axis, so I'll just make point 3D inherit from point 2D.
It feels efficient because you're reusing the X and Y code. But logically, it's completely flawed.
Because it inherits everything.
Right. If point 3D inherits from point 2D, it inherits all of its methods. What if point 2D has a method called getAngle that calculates the angle from the x-axis?
Okay, in 2D space, that's just one angle.
Exactly. But in 3D space, you need two angles, azimuth and elevation. If you call getAngle on a 3D point, it returns a mathematically meaningless result.
You've exposed a capability that makes no sense in the new context.
Precisely. You've broken the logic.
So instead of inheritance, you should use object aggregation, composition over inheritance.
Exactly. Instead of the 3D point being a 2D point, it simply contains a 2D point secretly inside its own black box.
Oh, so it just delegates to it.
Yes. It delegates the X and Y math to that internal component, but handles its own public interface for the Z-axis. You get the code reuse without the rigid, broken relationship.
Here's where it gets really interesting. The ultimate proof of why human intuition fails at inheritance is the famous rectangle and square surprise from the text.
Oh man, it is the quintessential cautionary tale of object-oriented design.
It really is. So in basic geometry, a square is a rectangle.
Unquestionably.
It's just a specialized rectangle where all four sides are equal. So naturally, an engineer writes a rectangle class with independent length and width properties. Then they create a square class that inherits from it.
Which passes the human intuition test perfectly.
Perfectly. Until you trace the memory state during execution. Imagine you have a complex graphics engine, let's say a prism rendering class. This class takes in a shape, and it performs a highly specific volume calculation.
Okay, tracking with you.
The algorithm inside the prism explicitly sets the shape's length to 5, and then sets the width to 4. For a standard rectangle, the underlying math churns through those independent axes and yields the expected geometric volume, say an area of 20 for the base.
Right. 5 times 4 is 20.
But what happens when the graphics engine passes a square into that exact same method?
Well, because a square is a subclass of rectangle, the compiler allows it. The engine just thinks it's operating on a normal rectangle.
But to maintain its nature as a square, the square class had to override those setter methods. So when the prism's algorithm calls setLength, the square's internal logic says, I'm a square, so I must also set my width to 5.
Uh-oh.
Exactly. But then the very next line of the algorithm calls setWidth. The square intercepts that and forces the lengths back down to 4.
So now they're both 4.
Right. The prism's algorithm, which relies heavily on those two axes being 5 and 4 respectively for its formula, suddenly runs its calculation on a 4 and 4. The math evaluates to a completely astonishing result, like a volume of 14 instead of what the algorithm anticipated.
It's a silent, catastrophic failure of internal state. And it happens because the design violated a core tenet, the Liskov substitution principle.
The Liskov substitution principle, or LSP, formulated by Barbara Liskov.
Yes. It dictates that if a program expects a parent type like our rectangle, substituting a subtype like R square must not break the program's logical expectation.
The principle of least astonishment.
Exactly. The rendering engine was astonished by the result because the square violated the rectangle's class invariant.
And just to clarify, a class invariant is basically the foundational truth of that object's data, right?
Yes. For a rectangle, the invariant is that the length and width can vary independently of one another. That is the contract it makes with the rest of the system.
Right.
By logically linking them together, the square destroyed the invariant of its parent. It literally lied to the system about how it behaves.
Okay, so if our intuition is actively leading us into these traps, how do we enforce these invariants? How do we build guardrails so our systems don't quietly corrupt their own data?
Well, we establish mathematically strict rules of engagement using design by contract, a methodology coined by Bertrand Meyer.
Design by contract, or DBC. It treats every function or method like a legally binding agreement between a supplier, the method being called, and a consumer, the client calling it.
Right. Every contract has preconditions, what the method demands as input before it will execute, and postconditions, what it guarantees as a return state after it finishes.
And this is where the rules for overriding methods and subclasses get really specific and honestly a bit counterintuitive. To safely override a parent's method, the text says you can only weaken preconditions, and you can only strengthen post-conditions.
That's the rule.
Yeah, let me challenge this. If I'm building a robust, secure system, why on earth would I want weaker rules on my inputs? Doesn't weakening a precondition invite bugs?
It sounds reckless, I know, until you look at it from the perspective of the client calling the code. We aren't talking about weakening security. We're talking about type safety and contract fulfillment.
Okay, give me an example.
Imagine you are a consumer who has an established contract with a supplier. The old supplier required you to submit forms in triplicate using blue ink, a very strict precondition.
Okay, a rigid input requirement. Got it.
Now, a new supplier, the subclass, takes over the contract. They tell you, I'll accept forms in triplicate, but I'll also accept digital PDFs. They've weakened the precondition. They're demanding less strict criteria. Does this break your existing workflow?
Well, no, because I can just keep sending my triplicate blue ink forms,
Yeah.
and the new supplier will still process them. My system doesn't crash.
Exactly. The client's original logic is perfectly preserved. But if the new supplier strengthened the precondition, if they said, I now require forms in quadruplicate using only red ink, your existing system completely breaks down because you can't fulfill the new demand.
Oh, I see. So subclasses can only weaken preconditions.
Exactly. It ensures backward compatibility. And strengthening postconditions works the exact same way. The new supplier says, the old guy promised delivery in 3 days. I guarantee delivery in 24 hours.
They're promising more.
Right. My system, which is patiently waiting 3 days, is not going to break if the data arrives early.
Yeah.
But if they weakened the postcondition and took a week, my whole pipeline stalls out.
So weaken preconditions, strengthen postconditions. It is the absolute mathematical guarantee that the Liskov substitution principle remains intact, preventing squares from masquerading as rectangles.
If we connect this to the bigger picture, all of these rules, the interfaces, the substitution principles, they are the building blocks of the famous SOLID principles of object-oriented design.
Right. SOLID is the acronym that gathers these best practices. We've hit on the L with Liskov substitution and the I with interface segregation.
But the culmination of all this architectural effort really rests on the D in SOLID, the dependency inversion principle, or DIP.
DIP. This is the ultimate weapon against code rigidity. It states that high-level modules, the core business logic of your application, should not depend on low-level details, like database queries or specific formatting. Instead, both the high-level and the low-level should depend on abstractions.
Exactly.
Let's ground this with a painfully common real-world failure from the text: the pricing factory nightmare. Imagine an e-commerce application calculating the final sale price of a cart. If you ignore dependency inversion, a junior developer will just write a massive, sprawling if-else block hard-coded directly into the main checkout module.
Oh, we've all seen this code. It reads like a chaotic novel. If the product is item C, multiply the unit cost by 1.3 to add the markup, then check if it's shipping internationally to add a processing fee.
Else, if the product is item D, apply the wholesale discount, but strictly subtract the promotional coupon. Else, if item, flat fee of 150 plus liability insurance.
It goes on for hundreds of lines.
And why is this so catastrophic? Because every single time the marketing team introduces a new product tier or tweaks a discount rule, you have to surgically open up the high-level checkout logic, the most critical part of your app, to modify this fragile list.
You are constantly risking breaking item C just to add item. It violates the open-close principle, the O in SOLID.
Open for extension, close for modification.
Exactly. Your architecture should be open for extension, meaning you can add new behaviors, but strictly closed for modification, meaning you don't have to rewrite existing tested code to do it.
So we applied dependency inversion. We rip all that messy product-specific math out of the main checkout module. We hide it behind a factory pattern at the very bottom of the system.
Yes.
The high-level checkout app now knows absolutely nothing about item C or item D. It just has a reference to an abstraction and iProduct pricing interface.
You've inverted the dependency arrow. The checkout module just asks the interface, what is the final price for this item?
And the factory handles the rest.
Right. The factory at the bottom instantiates the correct specific object for that product type. That object performs its own hidden mathematical gymnastics and simply returns the final decimal number back up the chain.
We successfully delayed the decision-making, just like we did with the Java collections earlier. The main application refuses to care about the specifics of the pricing until the exact millisecond it needs the final number.
It creates a loosely coupled, highly resilient system. When the business demands a completely new pricing model tomorrow, Your core checkout logic doesn't flinch.
You just write one tiny new pricing class?
Yep, have it implement the interface and drop it into the factory. The core system extends its functionality without a single line of modification.
So, what does this all mean? We've traced the entire arc of object-oriented philosophy today. We started by recognizing that even the CPU relies on data abstraction to shield us from the complexities of binary memory allocation.
The primitive.
Right. We took that concept and scaled it up, building polymorphic interfaces that allow us to seamlessly swap out heavy back-end engines without disrupting the application.
We explored the dangers of trusting human taxonomy over machine logic.
Proving that inheriting behavior like a square, forcing a rectangle's dimensions, can utterly destroy class invariance and mathematical certainty.
Astonishing the rendering engine into spitting out garbage data.
Seriously. And finally, we established order by enforcing strict design by contract rules, weakening our inputs and strengthening our outputs, and utilizing dependency inversion to protect our vital high-level policies from the chaotic, ever-shifting details of low-level implementations.
When you combine these practices, software stops being a fragile house of cards. It becomes a sustainable architecture that can actually evolve over decades without collapsing under the weight of its own technical debt.
And the beauty of this deep dive is that even if you never write a single line of Java or C# code in your life, these are incredibly powerful mental models for systems thinking and leadership.
Oh, absolutely.
Protect your high-level goals, your personal interfaces from the chaotic, low-level details of how they must be implemented every single day. Practice dependency inversion in your management style. Delay your rigid, binding decisions until you absolutely have to make them, preserving your flexibility to adapt to new facts.
You define the contract,
Right.
and you trust the implementation to work itself out.
I want to leave you with a final thought to mull over, applying this directly to your own life. Think about your current role, whether that's in an office, on a team, or within your family. If you are mapped out as an object in an architectural design, how many separate, distinct interfaces are you actively trying to implement right now?
Are you the manager, the mentor, the crisis mediator, the financial planner?
And more importantly, are you accidentally violating the Liskov substitution principle? When people interact with you expecting you to behave like your foundational base class, are you astonishing them by suddenly changing the rules of the contract?
That is a phenomenal question. Are you maintaining your invariance, or are you breaking the expectations of the system around you?
Definitely something to analyze. Thank you for joining us on this deep dive into the underlying architecture of logic and design. Keep questioning the structure of the systems around you, both digital and physical, and we will see you next time.